Coulomb's law says if you take two charges, doesn't matter if it's same charge or opposite charges. Let's say we have a charge here, and we have another charge right here. This has a charge, we'll call it, what? Q1. This has a charge, we'll call it Q2. There's a force between them. There's a force between them, and the value of the force is K times the absolute value of Q1, the absolute value of Q2, divided by the distance squared. The distance from here, the center of this, to the center of this. That's what Coulomb's law. K is a constant. 8.99 times 10 to the 9th. A lot of times you'll see me write that 9 times 10 to the 9. That's 8.99. It's a constant. Now we said the absolute value. Force is a vector. So what is the direction of that force? Because these two are, if you look at the picture, what kind of forces are there? I mean, what kind of charges are there? Same charge, right? So if you have the same charge, you know from magnet, if you take two charges the same from magnet, put them next to each other, what would you feel? You feel a push force. They're pushing away from each other. So the force here, this will be going in that direction, and this will be going in this direction. They'll be pushing away on each other. On the other hand, if you have opposite charges, that's the saying, opposite attract. You probably heard that. This will be pulling on that, and this will be pulling on this. So opposite charge is going to attract each other, they're going to pull on each other. And if this one can move, we'll move it closer to this one. When they're the same charge, they push away on each other, and they don't want to be next to each other. So if I have, again, two positive charges, which way the direction of the force? Pushing away. F will be going this way and that way. If I have a positive and a negative charge, these are opposite. They'll be pulling on each other. That's why this one says the magnitude of F. The direction, you're going to figure that out yourself, which way it's going to be. Using the magnitude of these. And if you have two negative charges, that's still the same charge. If they're the same, they're going to repel. They're going to push away from each other. Now we'll start with two forces, then we'll make that three forces, see what's going on there. Let's take an example here. Now to get a 1 Coulomb charge is almost impossible. That's a huge charge. So a lot of times we'll use micros and nanos. Micros 10 to the minus 6. Nanos is 10 to the minus 9. So let me take an example here. Let's say we have two charges. I'll make this one up. Plus or minus, what do you want?
Plus.
Plus. What's the value? 3.2 microcoulomb. Next charge, plus or minus? Minus, okay. 4.7 microcoulomb. I'm just making numbers up. Let's say the distance between them. The distance between them is, I don't know, 0.2 meters. What is the force? Well, first the direction of the force. For this one's going to be pulling on that one. This is going to be pulling on that one. They're going to be pulling toward the center of each other. And the value of that force, according to Coulomb's law, is K times Q1, Q2, over r squared. K is 8.99 times 10 to the 9. Q1 is 3.2 times 10 to the negative 6. Micros 10 to the minus 6. The other one, 4.7 times 10 to the negative 6 divided by the distance squared. (8.99) e to the 9 times 3.2 e to the negative 6 times 4.7 e to the negative 6 divided by 0.2 squared. And the value of that is 3.38 Newton. We got a force pulling on each other, the value 3.38 Newton.
Would you have to do 0.2 divided by 2
Which one?
for the radius?
It's a distance from here to there. That's what R here defined as. The distance from, they probably are, does our book use R or D? Yeah, radius not like this, not diameter, but like the distance between them, that's what R is. Let's see if our book use D or, I think it should confuse. They use R squared, but it's really the distance from the center to center. Now let me change that problem a little bit there. Let me change the problem. The same two charges now. I'm just going to put the negative charge on this side because I screwed up. I should have just centered it in the middle of the page there. This is microcoulomb for both. And the distance between them, still 0.2. The question I have for you, I want you to think about this one now. I have a third charge. And somebody chooses that charge, how the value of it. There's positive or negative first. What do you want that charge?
Positive.
Positive. And how big that charge? 2.8 microcoulomb. I got a 2.8 positive charge with me. I need to put the charge anywhere here. Hopefully there's a spot where if I put it, the net force is 0. Somewhere along this line, I want you to think, where should we put that charge such that the force, if possible, I don't know if it's possible or not, we just made these things up. Somewhere along there, can we find a spot on this line where we can take the 2.8 and put it and end up with a net force of 0? Could I possibly put it here? Let's think about this. Could it be here? Between these two charges? To me, the answer quickly, no. Why? If you put a plus charge here, what will happen? What is this charge going to do to that charge? It's going to push it. It's going to push it in this direction. And what is this charge going to do to that charge? Since this is negative, that's positive. What? Is going to pull it, opposite. Same charge, right? So anywhere in between, the two forces are going to be pointing in this direction. If you want the net result to be 0, that means they have to cancel each other out. So it can't be between them. It can't be. No way. Could it be on this end? Let's see. This is negative, that will pull on it, right? This is positive, this one is positive, it's going to push on this one. The problem with this scenario, it looks like it could happen here. It will not happen here. The reason? Because this charge is bigger and you're closer. That force will be much larger than this one. So if it's going to happen, it will have to be on this side. Not on this side, it has to be on that side. So not here and not here. It could be somewhere here. Because this charge is bigger than that, but it's farther. So if it's bigger, it's going to make the value bigger, but because it's farther, it's going to shrink it. So this is going to push on it in that direction. We'll call this Q1. This is Q2. So Q1 is going to push it in this direction. We'll call that force F1. Q2, I'm sorry, I drew them backward. This is negative. What is it going to do? Q1 is negative. This is positive. It's going to pull on it. This is F1. Q2 is positive. That's positive. It's going to push on it. That's F2. So if it's going to happen, it's going to be on this side of the table. So let's call this distance here from here to there x. And let's see if we can find what x is. What is F1? F1 is the effect of this charge on that one. I'm not looking at this, on that one you're putting there. So the value is going to be K times, what is Q1? 4.7 micro. I'm going to just write micro. What's this charge here? 2.8 micro over the distance squared. What's the distance from here to here?
We don't know.
Well, we know this is x and we know this is 0.2.
Oh, I didn't see that.
So what's the distance from here to there? 0.2 plus x. And let's look at F2. F2 is this positive charge pushing on that one. So it's K times Q, which is 3.2 micro, times 2.8 micro over the distance squared. And what is the distance from here to there? Square it, x squared. So what do you want these two forces to be? Don't you want them to be equal to each other? So I want F1 to equal F2, so for the net result to be 0. I want to cancel each other out. Plus, not times. And I left it as K intentionally because I know it's going to show up on both sides, so I don't have to deal with that number, just cancel it. And I left the mu here on both sides because they cancel each other out. So mathematically, I'm okay there. 2.8 times 4.7. 13.16. Three 3.2 times 2.8, 8.96. And now I need to solve it for x. Probably the easiest way to solve this for x right now is take the square root of both sides. Because if you take the square root, instead of foiling this one, I would have a quadratic equation. Take the square root. Take the 13.6, take the square root of that. And that's 3.63 over 0.2 plus x, the square root of something squared, you just drop the square. The square root of 8.96, 2.99 over x. Now we can cross multiply. .63 times x equals 2.99 times 0.2 plus x. 3.63x equals 2.99 times 0.2 move all the ones with x to one side. 3.63 minus 2.99 0.64x equals 0.598. What's x equal to? 0.598 divided by 0.64, 0.93 meters. So if you put that charge 0.93 meters from this to the right, the net force acting on that will be 0. The net force will be 0. Let's talk about that net force. Now let me draw here a picture. And here's a charge here, and here's 1. We're going to make this charge maybe positive, 2.4 microcoulomb. And let's make that charge what? Positive or negative?
Positive.
Positive what?
3.4.
3.4 microcoulomb. Okay. In my hand here, I'm going to take a negative charge. No reason I picked negative, just to be different. Let's say this is a triangle with equal sides. All sides are equal. What's the side of each? What do you want to give it a side for the triangle? Lengthwise, from here to there. 0.8 meters. Equilateral triangle. And how big this charge? That's a negative charge. What do you want that charge to be?
4.2.
What is it?
4.2.
4.2 microcoulomb. And what's the net force on this charge? We'll call it charge 3. This is Q1, Q2. And this is Q3. So the question, what is the net charge, the net force on Q3? acting on Q3. Okay. What is Q1 doing to Q3? Is it,
Together.
huh?
They're pulling.
Pulling, so if Q3 can move, it's going to move in this direction, Jonathan said. Let's call that force F13, 1 acting on 3. And what is Q2 doing to Q3?
Pushing it over.
Pushing it which way?
Away from the charge.
Why would it push it away? 2 to 3.
Oh, negative, sorry. Attract.
That's going to be pulling in that direction. We know the angle between them here is 60 degrees. That's an equilateral triangle. We know this angle is 60. We know this angle is 60. That comes in later. So let me find what F13 is and F23. K times Q1. When I say that's the absolute value. Q3, I'm just tired of putting absolute value over R squared. So that's 8 point, I'll just go 9. It's 8.99 times 10 to the 9, or 9 times 10 to the 9. I'll just make my life easy. 9 times 10 to the 9. Q1 is what? 2.4 micro. Micro is 10 to the minus 6. Q3, 4.2 micro. Notice I don't use plus or minus. Over the distance squared, 0.8 squared. Again, the micro here, 10 to the minus 6. Don't forget that. 9 e to the 9 times 2.4 e to the negative 6 times 4.2 e to the negative 6 divided by 0.8 squared. F13 is equal to 0.142 Newton. Let's find F23 now. Nine point oh times 10 to the 9. Q1, Q2 and Q3, I'm sorry. Q2 and Q3. I did the 1 and 2. Q2 times Q3. Q2 is what? 3.4 micro. Q3 is what? 4.2 micro. Divided by R squared. And I got 0.201 Newton. Now I get two forces. I need to find the net result of them. I got a graph paper here, perfect. Good, there's a couple sheets here, I can use that. Here's what I have. If I draw my axes right here, X and Y axes, I got one force in this direction and I got one force in this direction. This force here has a value as F23.201, and this angle with it is 60 degrees. Why? Notice if I do my axes right here, it's now geometry. If this is 60 degrees, that's 60 degrees. The angle between these two is 60, so from here to there, that's what, 120? This angle is 120 degrees. Well, because we measure them negative when you travel in that direction, so if you want to use negative, that's fine. And the value of that force is what? 0.142. And now I want to find the net result of these two forces. This is going back to physics 1. You get two vectors, you're trying to find the net result. Remember how we did that? In 3 steps or 4 steps. My group here probably going to remember this once I draw it quickly. We have 3 columns. The first column, second column, and the third column. The first column is going to have the vector in it. Second column is going to have the x component of the vector. And the x component is always going to equal r times cosine theta. And the y value is r sine theta. So the first vector I'm looking at, I'll look at this one, 0.201. The angle is what, negative 60? So the x value is going to be 0.201 cosine of negative 60. And the y value 0.201 sine of negative 60. Negative 0.191. And the y value I might be in radian mode because that gave me a positive value. That doesn't make any sense. I might be in radian mode and this doesn't make any sense. Let me just check my mode on the calculator. Where's mode on this calculator? Mode. Yep. I need to be in degree mode. Okay, let me redo that number. 0.201 cosine negative 60. 0.101. It's not a negative, it's positive. And the y value 0.201 sine of negative 60. That should be a negative value. Negative 0.174. Now I gotta look at the other vector. And the other vector is 0.142 and the angle is negative 120. Notice I always measure my vector from the positive x-axis. If you do that, that will take care of all the plus and minuses. So this is 0.142 cosine negative 120, 0.142 sine negative 120. 0.142 cosine negative 120, negative 0.071. And 0.142 sine negative 120, negative 0.123. So we always broke the vectors into x and y component for each one. Now the result, we're going to add them. In the x direction, the result is, and in the y direction, the result is. I call them r sub x and r sub y. R for result. The result in the x direction, we take this number, add it to this number. The result in the y direction, this one, add it to that one. Point 0.03. The result in the y direction, 0.174. 0.123, add them together, that's a negative . This is what I'm looking at. The result in the x direction is positive. The result in the y direction is negative. So my answer is going to be this vector. This is what my answer is going to be. Which quadrant? Quadrant 4. So I'm okay. Because if you're in quadrant 2 or 3, you have to add 180 degrees to your answer. So r is going to be the square root of the x value squared plus the y value squared. This is dead. So let's see what that number is. And if I did my math correct, that's 0.296. And theta is going to be the inverse tangent of the y over x. Y here is what? Negative 0.294. X is 0.03. And it's negative 84 degrees. So the net result is 0.296 Newton. This is Newton. The direction of that is going to be 84.2 degrees negative in that direction. That's what the net force is. One more example of these, then we'll take a break and come back to talk about electric field. Let's make it more fun now. I get this piece of I have paper. Let's make it a square there. We'll put 3 charges in it. Three. Yep. We have a square. I'm going to put 1 charge right here. 1, 2, 3, 4. Put another charge here. Put 1 here. And no charge down here. Q1, that's this one in the bottom here. I'll make the charges of positive 2.9 microcoulomb. I'm going to make them all the same charge. Make my life easy. Q2, 2.9 positive, again, 2.9 micro. Q3, positive, 2.9 microcoulomb. And the distance for this box, side to side, is 0.5 meters. So this is 0.5 meters. 0.5 meters square there. So I took the edges of a square, basically like this. And I put these three charges. I didn't put one here, I just put three charges. You know what? Let's put a fourth one here. Same charge. And the question is, what's the net charge on net force, I mean? What is the net force? You pick one of the charges. Which one? 1, 2, 3, or 4?
3.
3. Okay. Let's look picture-wise. What's happening there? 1, Q1 on 3. They have the same charge, both positive, so they're going to repel. 1 is going to be pushing Q3 in that direction. F1 on 3. What is 2 going to be doing to 3? Same charge. It's pushing away on it. What is 4 doing to 3? Same charge, pushing away on it. And that's what's going to happen. Let's find each one, then we'll go and do some trig and find what the net force is. We know this is 0 degree, we know this is a 45 degree. You know, that's 45 square there. And that's a 90 degrees if you do x and y axes right there. So let's find F13 first. K times Q1, Q3 over R squared. Well, R is a problem here. What is that distance from 1 to 3? What's that distance from here to there? Let's call that C. Don't you have a right triangle there? Pythagorean's theorem, C squared equals what? A squared plus B squared. So what's 0.5 square plus 0.5 square? And C is the square root of that number. 0.70, C squared is 0.5, or C equals 0.707. So let's see what F13 equals to. 9.0 times 10 to the 9. Q1 is 2.9 micro. Micro is 10 to the minus 6. 2.91 micro over 0.707 squared. 9.0 e to the 9 times 2.9 e to the negative 6 squared divided by, that's 1 Newton, not 1. 0.15138. So I'll go 3 decimal places. F2 on 3. 9.0 times 10 to the 9. 2, which is what? 2.9 micro. 3 is 2.9 micro. 0.5 squared. And I got that's not right. Is it 0.30? 303, I think. And what's F4 on 3? And that's going to be the same as this. And now I got all my forces. And I just got to find the net result. Then I'm done with it. Let me draw these, clean them. This is what I'm looking at. I'm going to enlarge the forces. I got the first one, Q1, that's F23 in this direction, which equals, where's my number? 0.303. I got F13, a little bit smaller, in that direction, 0.151. And I got F43 up there, which is 0.303. These are my 3 forces, and my job is to find the equivalent value. Again, I got to find the x and y component for each one of them. I'm going to use the same process I used 2 minutes ago. The vectors, x component, which is r cosine theta. The y component, again, make sure you calculate in degree mode. The first vector is 0.303 angle 0. That's 0.303 cosine 0, which is 0.303. The y value 0.303 sine of 0, which is 0. The second one, 0.151 angle 45. 0.151 cosine 45, 0.151 sine of 45. Point 107. 0.107. And the last one, which is 0.303, angle 90 degrees, the one going upward. That's 0.303 cosine 90, and that's 0. 0.303 sine of 90, and that's 0.303. So we found the x and y component for each one of these vectors. Now the result. I want to get the result in the x direction, and I want to get the result in the y direction. .410. So again, looking at it, which quadrant am I going to be? It looks like quadrant 1, I'm good. If I'm in quadrant 1, I got an x value in this direction. I got a y value in this direction, and the net result going to be in the first quadrant. This is what the net result is going to be. And this is what theta is. This piece is r sub x. This is r sub y. So I know I'm in the first quadrant, which means I'm good with my angle. I don't have to adjust it. So to get r is going to be the square root of the x and the y value squared. .47 Newton. And to get theta is going to be the inverse tangent of the y over the x. And that's 45-degree angle. So if you put these equal forces there, the net result will be one force in that direction. This is the value of it. That's the angle of it. And that's the end of this problem.